Okay, Dr. Matthew J. Trom here. We are into a new module, which is multidimensional and transient conduction. And this is for the course lecture 6, multi-dimensional steady state conduction. Yahoo. All right. There are corresponding readings. This is all of chapter 4. So 4.1, 4.2, 4.3, 4.4, 4.5. Please read all of those in the book. And then for those of you seeking the ADA compliant transcription, once I finish recording this, I will go back into the original PowerPoint presentation and I will put the link here so you can click on that and get to the transcription if you're looking for it. Okay. Let's get going. All right. So, you guys know that I like to start my lectures and presentations with memes, cartoons, and so forth. One of you guys, you know who you are, sent me this, which I thought was hilarious. To be fair, this is fluid, it's not heat transfer, right? But come on, it's all the same stuff. Here's like a newborn and then here's the Navier-Stokes equations. And, someone's clearly doctored this so that I'm not sure what it is that they were actually showing, probably grandma or something like that. But now this kid is getting indoctrinated into fluids at like age 2 days. So teach them young, which, um, you know, you guys are young. So I thought this was funny. Anyway, okay, let's let's get into it. All right. So we spent a ton of time talking already about one-dimensional conduction. And in that conversation, we derived, or sort of kind of derived, right? I pointed out that it's in the book, and I kind of gave you the 64,000 foot view for the heat transfer equation, which is this, right? Which comes from the first law of thermodynamics. And up until now, we basically just crossed out everything that wasn't dt dx, and it kind of collapsed into a one-dimensional equation. So the world is not one-dimensional, right? As nice as that would be. And so we're gonna now expand out into at least a second dimension, 2 dimensions. And so I say here for constant thermal conductivity, steady state, zero energy generation, and thin geometry. So thin geometry is kind of the key operative word here. So for thin geometry, we're still going to take this derivative with respect to z, and we're going to ignore any temperature gradients with respect to z, because we're going to imagine basically a perfectly thin flat plate, right? So because it's perfectly thin in the z direction, there's no way for any sort of temperature gradient to be sustained in the z direction. So that term is still gone. But we're going to allow the y derivatives now to exist and not be zero. And so, with no heat generation and everything in steady state, the heat transfer equation collapses into basically Poisson's equation, but now in 2 dimensions instead of one. Um, so we have second derivative temperature with respect to x, and second derivative temperature with respect to y. Those sum together and equals zero. That's the equation that we're going to be solving, at least in the beginning here, for 2 dimensional heat transfer. And remember, right, our goals for heat transfer analysis remain the same, right? So same goals, just more dimensions. So first and foremost, we want to be able to solve for the temperature field, T as a function of X and Y and Z, right? So basically the temperature anywhere on this imaginary flat plate that I've been talking about. And then once we have the temperature field, we want to be able to determine the heat flux in all directions, right? So heat flux in the X, the Y, and the Z directions, presumably. Um, so for multidimensional heat transfer, which is what this entire lecture, this entire chapter is about, we're going to talk about three different approaches, right, to basically solving this, or more complicated, as we'll see, more complicated versions of this. The first one, which I love, it is so cool, you'll see, is the exact solution. The second approach is so-called approximate or graphical methods. And then the third one is called numerical methods. So we're going to kind of march through all three of these in the next 40 some odd slides. Okay, so let's change slides. Okay, so first, as I mentioned, is exact solutions, right? So let's jump into the exact solutions. Um, so this is a differential equation, right? Second order differential equation of two variables. And so it can be solved. It's just 2D Laplace's equation, and the solution to that is known. So once you solve the 2D Laplace's equation, now you have temperature as a function of x and y, right? Remember, z is very thin in this kind of two-dimensional world that we're talking about, thin flat plate. So we don't need to worry about the temperature in z. It's constant in z for any combination of x and y. But once we've got that temperature field solved, we're then going to use the fact that heat flux is perpendicular to the isotherms, which we learned back from one-dimensional conduction, and we're going to use that fact to determine the heat flux in the x, the y, and the z directions. So what this kind of looks like graphically is we have our isotherms, right? So here, let's start here. Isotherms, right? So isotherms are lines of constant temperature. And then we have our heat flux, right? So you can actually see that the heat flux, this is the arrows, which are telling us that the direction of the heat is moving through this object. And it is true that the heat flux is always perpendicular to the isotherms, right? So that's kind of this line here is our isotherm. This is like zoomed in, right? So zoomed in, right? Here is the heat flux. Here is that perpendicular relationship between the heat flux and the line of constant temperature. And then, of course, the heat flux can be broken into components in the x direction and the y direction, which is what I'm talking about here. Q double dot double prime XYZ. This is just each of those individual components, right? So QX, QY, there they are. And then you add them back together, and you, of course, just get Q double dot, which points again in a direction perpendicular to your isotherm. This particular setup, we have an adiabatic surface here on the bottom. We have another adiabatic surface here on the top. We have a line of constant temperature fixed at T1, an isotherm at T1, which is basically this vertical line here. And then we have this other line, which is also an isotherm, constant temperature at T2. And notice we have kind of this two-dimensionality, right? So two dimensions here. These lines of heat flux are basically curving because this line is vertical and this line is more kind of a trapezoidal shape, right? And so it's going to create this kind of two-dimensional temperature field, which is then going to create a two-dimensional heat flux, at least in terms of its direction. So pretty cool. Okay. So, exact solution techniques are available, as you will see in a second, but they do involve complex mathematical series and functions. This is why we have you take linear algebra and differential equations and calculus and all those cool math classes that you took, because by now you should know how to solve equations like this even in two dimensions and get the exact solutions. So hopefully what I'm going to show you on the next slide is going to look like something you've already seen in an advanced math class. The closed form solutions are restricted to simple geometries and simple boundary conditions. So we'll see. You could solve for things like, a flat plate, right? A rectangular flat plate. You could solve for a circular plate. You could solve for. But as things get complicated, the equations don't lend themselves well to more complicated geometry. So we're very limited in what we can actually do. But we can get exact solutions, and as we'll see, these exact solutions turn out to be quite valuable. If for no other reason, then you can use them kind of as a gut check to make sure that your solutions to more complicated geometries through those other two techniques are correct. So I say here, still, these solutions are valuable because they give a temperature field of XY. And probably most importantly, they are useful to compute the temperature at any point, right? We're going to end up with essentially a series of continuous functions. And so anywhere in this shape, if we know the boundary conditions, right? We know this temperature, we know this temperature, we know this is adiabatic, that's adiabatic. So we know all the boundary conditions. We can determine any arbitrary point, it doesn't matter where it is, and solve the heat transfer equation and find the temperature at that point. So it's a very, very powerful outcome, which is actually only true for the exact solutions. All of the other techniques that I'm going to describe, you can solve for a temperature, but it's only at a particular point. You'll see. We'll get there. Okay, I got to figure out how to change slides. There we go. All right. So how to solve that Poisson's equation? Well, there's several different techniques. The one that's used in our textbook is called separation of variables. If you've taken like an advanced differential equations class, or back 1,000 years ago when I was an undergrad, the class that I took was called engineering analysis. It was actually taught by an engineering professor, Bill Serignano at UC Irvine. I still remember his name. It was like awesome, right? Because it was finally an application to all this ridiculous math that we had been doing for the past 2 years, right? All the calculus and all the prerequisites, right? And all of a sudden it's like, hey, you want to know the temperature field on a plate? Well, here's why you learned how to solve this, differential equation with separation of variables. It's because that's the answer to the heat equation, right? So pretty cool finally to be able to connect all that stuff together. So how does this technique work? Okay, so we've got a thin rectangular plate. We're going to say that it has a length L and a width W, right? So here's our plate, length L, width W. And we're going to, just for purposes of this particular derivation, we're going to set three sides at a constant temperature, which is called T1, right? So here's surface 1 at T1, here's surface 2 at T1, here's surface 3 at T1. And then there's going to be a fourth surface, which is maintained at a different temperature, which we'll call T2. And that temperature is not equal to T1, right? So this surface up here is at T2, temperature 2, right? This would be a really boring problem if these were all the same temperature, right? Because remember, we have no heat generation, right? It's Poisson's equation, no heat generation. So if all of these surfaces were at constant temperature and they were all the same temperature, there'd be no temperature gradient, right? It'd just be all the same temperature all the way through. So that is a solution to that particular set of boundary conditions for Poisson's equation, but that's like super boring. No. We want to set different temperatures at these different surfaces, these different edges, and figure out what that does to the temperature field inside the plate. So that's where we're going with this. Okay, and then I say here, we're going to neglect temperature gradients normal to the XY plane, right? So that's like into the page and out of the page, which is basically what I said before. This is a thin plate, and so any derivative with respect to the Z direction, which is into the page or into the screen, is equal to 0. It's a two-dimensional problem. Okay, I'm now going to do my, I think you guys have heard me describe the law of conservation of chalk before, right? Which is the idea that you just kind of get tired of writing big, long equations over and over again. So you set the big, long equation equal to something else, and then you use that something else all the way through. And then in the very last step, you like undo what you did in your law of conservation of chalk. So that's what we're going to do here. We're going to define this thing called theta. And theta is just a ratio of temperature differences. So it's in the numerator, it's the temperature of any spot on this plate, right? Txy, the temperature field, minus T1, which is the lower of the two temperatures, right? So the temperature here, and there is T1. And then that's going to be essentially non-dimensionalized by T2 minus T1, which is the biggest possible temperature difference that you could get for this particular configuration, right? Remember T2, that higher temperature is up here. And so high temperature, low temperature, low temperature, low temperature. And we're going to refer to that as theta. It's like a dimensionless temperature. Notice that theta, if I set it up this way, goes from 0 to 1, right? So anytime I have a temperature of T1, like all the way around the edges, theta is equal to 0, right? So that's why this says theta equals 0, this is theta equals 0, this is theta equals 0, because these temperatures are all T1. T1 minus T1 is 0. It doesn't matter what's in the denominator, so, we get 0. And then here, the hottest spot, right? Remember, it cannot get any hotter than this because we have no generation on the inside here, right? So this is the highest temperature we're going to see in this entire plate at T2. And so we're going to just plug in T2 for TXY along this surface. And now we have T2 minus T1 divided by T2 minus T1. Lo and behold, it's 1, right? So we have theta equals 1 here along this surface. And that's basically what I'm saying here, right? So 0 is greater than equal to theta is greater than equal to 1, or bounds on theta. Right. So again, theta is a number that goes from 0 to 1. A cool thing about this, right, is if I take a derivative with respect to x or a derivative with respect to y, what happens? Well, the derivative of this thing is just the derivative of the temperature, right? Because if I take the first derivative of this guy with respect to x versus the derivative of this guy with respect to x, it just comes out to be the same. This thing is a constant, falls away. So I can actually now take these derivatives from my Poisson's equation, right? Second derivative of t with respect to x, second derivative of t with respect to y. I can take a first derivative and then I can take a second derivative. And what ends up happening is these derivatives with respect to t are just equivalent to the same derivatives with respect to theta. So I can do this exact substitution from t to theta and just rewrite my Poisson's equation in terms of theta instead of t, right? It's basically, again, just a non-dimensional temperature, right? So I'm just substituting one kind of temperature for another, and this one just happens to go between 0 and 1. And then when I want to reverse this later on in the end, when I solve for theta, I'm just going to do the reverse of this, right? I'm just going to plug in the value for theta. I know T1, I know T2, and the only thing I don't know is TXY at that particular spot that I'm solving for. So that's super powerful technique. We're going to see this a lot. We do this a lot in heat transfer. We turn everything into theta and bound theta from 1 to 0 and then solve for theta. And then in the last step, we'll back out what the actual temperature is. It makes the math a lot easier, as you'll see. Now, of course, this is a second order differential equation with two variables, right? So we need 4 boundary conditions, 2 boundary conditions for each variable, 2 variables, 4 total boundary conditions. And hey, we have them already, right? Because we're given the temperature along each one of these boundaries. So theta at 0, comma y is 0. So let's see if we can figure out what that means. Theta at 0, comma y. That's any value of y, right? So that's here. Yeah. Yeah. Right. So x equals 0 and y equals any value of y. That's this surface. It's 0, 0. Okay, that works. Boundary condition 2 is x comma 0 is equal to 0. Right. So that's this, right? Yeah, any value of x, right? So it's all along this line at y equals 0. Yep, it's 0, 0. Good. Okay. Third boundary condition is theta at L, comma y. So L is out here, right? So that's x equals L is here, and then any value of y is this surface. So yep, that should also be equal to 0. Yep, it is. Okay, cool. And then this one, theta of x, comma w. Okay, x, so any value of x, and then, okay, L equals, y equals w is up here. Yeah, okay, right. So it's along this surface, right? And so that equals 1 and equals 1 here. So I've got those all set. The reason, by the way, that I've got this one in red is just to remind myself that these 3 boundary conditions, theta equals 0, 0, 0, 0. Those are all the cold surfaces. And then this guy, theta equals 1, that's the hot surface, right? So red for hot, I guess, is how I'm thinking about it. Okay, now here is where the hand wavy magic happens. Not really. I mean, this is a legitimate mathematical solution. But I think it's very kind of clever how they came up with this. I don't actually know how mathematicians came up with this, but it works. And we're engineers. We don't care about the math and how to figure it out. We just care about the solution and whether it works or not. So here's our mathematical magician, and the crux of this separation of variables idea is mathematical magician just says, okay, this thing that we call theta is going to be made up of 2 subfunctions. One is a pure subfunction of x, and the other is a pure subfunction of y, and they're going to be multiplied together. And that's going to give us our theta value. I don't know what capital X is. I don't know what capital Y is. They're just some function of X and some function of Y, respectively. But if I multiply them together, I get theta, right? And that's basically a guess that you're making. You solve the entire problem under this assumption, and you go back at the end to prove to yourself, yes, in fact, we do have a function that's only a function of x multiplied by a function that's only a function of y, and hey, I guessed right, right? So isn't math neat? So anyway, that's what we're doing. That's how this works. Okay, let's advance our slide. Okay, so mathematical magician is saying, okay, if I know that theta is a product of a function of x and a function of y, I'm just going to plug, let's go to previous, I'm just going to plug this equation, function of x times function of y, into my Poisson's equation, right, where theta appears. And what pops out of it is, well, here, I'm actually taking the second derivative, right? So I'm going to end up with the second derivative of this capital X function with respect to x, right? And then the 1 over x emerges from the derivative process. And then I'm also going to have, and notice there's a negative sign here. Why? Right? Because we're going to move one of these to the other side of the equation. So one of them gets a negative sign sitting in front of it so they can be equal to each other. But this one is, I'm just taking that same function of theta and taking its second derivative with respect to y, right? So here it is, right? Second derivative of y with respect to y. And out pops out a 1 over y, right? That's any constant that appeared in this function. And they're equal to each other with this negative sign sitting there because they were originally equal to each other here before I took the derivative, right? All I'm doing again is just plugging in my capital X times capital Y, and which are functions, and then I'm just actually carrying out this derivative, right? So that's what I'm doing here to get this equation. Okay, so and again, mathematical magician says this differential equation is separable. By separable, it just means you can separate the x function component from the y function component. Left side depends on x only, right side depends on y only, right? So here's the left side, which depends on x only. Here's the right side, which depends on y only. They're equal to each other. And because they are equal to each other, and this one is a derivative or a second derivative with respect to x, and this one is a second derivative with respect to y, your only choice, if you wanted to actually figure out what these things are equal to, is that they have to equal some constant, right? You don't have any other choice. That constant can't have an x in it, it can't have a y in it, because if it did, when you took the derivative of it with respect to the other variable, poof, it would go away, right? You end up with zero. So it must be some constant that these two things are equal to each other. And just for convenience, we're going to use lambda squared, and you'll see why, right? There's mathematical reason why you use lambda squared. It's because it makes the math easier. And we're specifically going to choose positive lambda squared, so that the solution satisfies the prescribed boundary conditions, right? So we're gonna choose positive lambda squared on purpose, so that when we plug this thing in, the boundary conditions work out, and we don't end up dividing by zero or taking the square root of a negative number, something horrible, right? So okay, so I know the solutions to x and y, right? Because I can solve this guy is equal to a constant, and I can solve this guy is equal to a constant, right? It's basically just a now second order differential equation with two boundary conditions here, second order differential equation with two boundary conditions here. So I know what those are, right? They happen to be equal to each other, but they also equal to a constant, which is lambda squared, so I can solve. And so here they are, right? So here is capital X is a function of X. It's C1 cosine lambda X plus C2 sine lambda X, right? You don't see any Y's in here, right? No Y's, because we're doing separation of variables, right? So no Y's in this function of X. Okay, and then here's Y, capital Y, right? It's C3 e to the minus lambda Y plus C4 e to the lambda. Ooh, that's not good. Okay. My guess is that is a typo. Let me write this down. Number 6. Okay. When you guys see this, that X will be a Y. I bet you I copy pasted this and I forgot to fix it. There should not, there definitely should not be a function of X in my pure function of Y, right? So that's a screw up. So good thing I caught it, or else, man, we would have a mathematical breakdown here. Okay, so this should be a Y. Um, Okay. Yeah. And remember, my original definition is that lambda, no, not lambda, theta of X and Y is capital X times capital Y. So I'm going to take these two guys. Here's capital X, here's capital Y, and I'm going to multiply them together, right? Because that's my separation of variables definition. And here it is, woohoo, in all of its glory, right? So here's my function of X. Here's my function of Y, and check it out. I messed up again, right? I just copy pasted this into this, and I made a mistake here, and that just carried over. So when you guys see the final slides, look at them in PowerPoint. This will be a Y, right? Because it's got to be a function of Y only. But they just get multiplied together, right? Okay, cool. So now we're going to find C1, C2, C3, C4. Those are all constants of integration that come out of taking two integrals of X equals lambda squared and Y equals lambda squared. Um, and we know the boundary conditions, right? We talked through what the boundary conditions are, so I just list them here again for your convenience and edification. Okay. Yep. Okay. So here I've just like oh dear God. Well, I've really screwed this up. here's another mess up, right? I've got Y here, which is right, and then I just copy and paste it for the previous slide. This should be Y. But here's that equation, right, with one little typo in it. Here's that equation. And then here's the boundary conditions, right? So just what I was talking about on the previous slide. And I am not going to walk through how you plug in the boundary conditions to actually solve for C1, C2, C3, C4. If you're really interested in how to do that, it's derived in the book. There's a lot of kind of weirdness about like, ooh, signs with N's in them, right? Because, N equals one or two or three or four or five, they're whole numbers. And so there's a whole explanation in the book for why that has to happen to make this the solution. Again, if you're interested, check out the book. I think it's fascinating, but you don't really need to know the underlying explanation why to get to the solution. So here we are at the solution. So this is it. This is the exact solution for theta, right? Which is basically, again, just the dimensionless temperature that represents the temperature field of our flat plate from before, right? So hallelujah, the magical magician has created for us this exact solution. Okay, now this looks awful, and my God, it is awful. It is awful, but I think it's also like one of the coolest parts of heat transfer is um, this is an exact solution for the temperature field of this flat plate that has different temperatures around the edges. But it's also an infinite series, right? So we start at n equals one and we go to infinity, and here's an n, and here's an n, and here's an n, and here's an n. You get a car, and you get a car, and you get a car, right? So even though this, you can write this, and this is truly the mathematically correct exact solution, you never can actually solve it because there's always another n, right? You can always use it. N equals 6, n equals 7, n equals 8, equals 9, equals 10. You can just keep going forever. And yes, those terms do get smaller. That's what I say here. Theta xy is a convergent series where the terms diminish in magnitude for higher n, but there's always a little bit more that you could get, right? A little bit more precision. It's like taking pi out to the billionth, decimal place. You could do that if you wanted to. But remember, we are engineers, not physicists, not chemists, not mathematicians. And what are the three words that define engineering? Good enough, right? And not three words, but two. You've heard this joke, right? Three words that define engineering. Good enough. So we usually just take enough of these ends to get ourselves to a level of precision that is good enough for whatever it is that we're trying to calculate. And so for an engineer, this is a perfectly good exact solution, particularly because it's convergent, right? And the higher you go in n, the smaller those little add-ons get. And at some point, you reach an n that's so small that it doesn't matter anymore, right? You get an answer that doesn't really change the end result from an engineering perspective. So the other really cool thing about this is, look, it's a continuous function, right? I can put in any value of X. I can put in any value of Y, and I can solve this thing for theta at any value of X and any value of Y. And, right now you guys are sitting there thinking to yourselves like, Trom, what the hell are you talking about? Like, that's true of every equation. Like, what? Why is that so cool? You guys will see in a second, right? We're going to get to the other solution techniques. And in none of the other solution techniques can you actually do this. You have to pick a particular discrete point that's basically forced upon you by the geometry of the problem. And you cannot find the temperature anywhere you want. You can only find the temperature at the spot where the formation of the problem wants you to find it. You'll see when we do finite element, finite difference. But this is a continuous function, right? So you can put in any value of X, any value of Y, and get an exact value for theta. I think it's very cool, very cool. Okay, now there are some discontinuities, right? Those discontinuities occur at the edges, right? So let's go back, and you can actually see this, right? So right here at this corner, theta equals 0, but theta also equals 1. And at that corner, those two solutions are both true. Same is true over here, right? At this corner, theta equals 0 from this line, and it also equals 1 from the top line. So there are a couple of discontinuities in this solution because of the boundary conditions. But in physical reality, those things are untenable, right? So there's those corners are kind of a special situation where when we solve the engineering problem, we don't worry about what's going on at the temperature of those corners because we specifically set the boundary conditions there, right? So don't need to worry about those discontinuities because they're not like physically present inside the real flat plate that we're trying to analyze, but just to be aware that they're there. Okay, so how cool is this, right? How cool is this? This is what it looks like. So, right, here's my constant theta equals 0, constant theta equals 0, constant theta equals 0. Here are my two discontinuous spots, right, which I told you I would point out. So we're going to ignore the temperature at this corner and this corner because those temperatures are simultaneously theta equals 0 and theta equals 1 because of the way we set the boundary conditions, right? Here's our theta equals 1. And then these curves are isotherms, right? So how cool is this? These are lines of constant temperature, and this is the exact solution from that function that I showed you on the previous slide, right? I mean, this is like stunning how cool and beautiful this is. And these are discrete values, right? So these are theta equals 0.75, theta equals 0.5, theta equals 0.25, theta equals 0.1. But there's like an infinite number of these for different values of theta interspersed between, these sort of, milestone values, right? And it doesn't just stop at 0.1, right? There's another isotherm at 0.05 and 0.005 and so forth. They go all the way down here. So I think this is so cool. Okay, so sorry, I'm getting like carried away. We actually want to find a temperature, right, at a particular spot. So I think, let me see, what spot did I pick? What spot did I pick? Huh. Let's see. Oh, here. Right. Okay. So, okay. So sorry. So here's the exact equation, right? We've now seen this a bunch of times. Here's what that solution looks like in, two-dimensional space. Here, just as a reminder, is what theta means. And for our purposes, to solve this little example that I've got on this slide, T1 is going to be 300 Kelvin, and T2 is going to be 400 Kelvin, right? So we're just going to set those values. And then I'm going to say, okay, I want you to find the temperature at X equals 0.5 meters and Y equals 1.5 meters if this thing is a square, right? Doesn't look like a square, but it's a square where L equals W equals 2 meters, right? So length equals width equals 2 meters. Okay, so where is that spot? Well, X equals 0.5, right? If this is the X direction and this whole distance is 2 meters, halfway through is 1 meter, and then halfway again is half a meter, and I go up, and okay, there's that spot. And then at Y equals 1.5, right? So this is the Y direction. This is about halfway, and then another half is here, right? Okay, so that's what this yellow spot is, right? Is It is the location x equals 0.5, y equals 1.5. Kind of just circle it there so you can see it. And just for you wouldn't normally have this figure in advance, but just to sort of give a sense, we're expecting a value of theta, right? These are theta values of a little bit less than 0.5, right? Because this is that isotherm, that line of constant temperature. Theta equals 0.5. So, something like 0.4, a little bit, is what we're looking for at this spot. But I can plug in any value I want, right? I just happen to plug in these two numbers, but I can plug in a value down here, over here, over here, over here, anywhere I want to find the temperature. Now, how do I actually find the temperature? Well, this is the painful part. So I have to go through and solve this thing for um, n equals 1, n equals 2, n equals 3, n equals 4, and so forth. And then add up all those values and keep going in n until I get um, oh man, I messed this up too. Okay, hang on. Write this out here. Um, I'm going to keep going until I get enough ends, enough values that I add them together, and my precision is out here to the third or fourth or fifth decimal place, and I don't really care anymore. Okay, so I screwed up over here. So I did it for the first one, right? So here I am intentionally plugging in. It looks like n equals 1. Yeah, n equals 1. Yeah, right here, theta of n equals 1. Okay, so I plugged it in. And I tried to put the n in parentheses so you could see it, right? So here's n, here's n, here's n, here's n, here's n, right? Compared to where n lives up here, n, right? Those get turned into ones. And then for x, where's x? So here's x, right? I'm plugging in my 0.5, 0.5. And then for y, which is here, I'm plugging in my 1.5, right? 1.5, 1.5. And I'm solving this guy for the first n, right? And if I actually solve it for the first n, I end up with 0.4076. Okay, but that's not the end of the story, right? So now I've got to put in n equals 2, and I got to do it again, right? So I didn't show that. That's what that's what this table was meant to show. I actually have this in Excel, and I forgot to fill in the values. What you guys will see when you put in even numbers is this first term, the coefficient out in front goes away, right? So what do I mean by that? So if n equals 2, this is 2 plus 1 is 3, which makes this negative 1 to the third power, which is negative 1. Negative 1 plus 1 is 0. This whole term sitting out in front is 0, which means the whole thing is 0 for n equals 2. In fact, all even numbers, that's true, right? Because any even number for n is going to give me an odd number for this exponent, which is going to make this whole thing equal to 0. So this column is right. N equals 2, n equals 4, n equals 6, n equals 8, and so forth. I'm just going to get 0, 0, 0, 0, 0, 0 the whole time. This column is wrong. So when you guys see the final version of these slides, I'll actually have numbers in here. I did the calculation. I just forgot to put the numbers in. Sleep deprivation, right? So I'll get a number here. It's going to be quite a bit less than 0.4, but it'll be non-trivial. I'll get a number here. It'll be less than that one, but still non-zero. I'll get a number here that'll be less than that one, and so forth, all the way up to n equals 9. And then I'm just going to sum up those values, right? So I'm going to sum up n equals 1, 0.4, n equals 3, 0.04, n equals 5, 0.004, whatever the numbers are. I'm going to add them all up. And this is the end result, right, of me summing up all of those, both this column, which is going to have numbers in it, and this column, which of course is all zeros, out to n equals 10. I get 0.4320 instead of 0.4321. It's like the combination on my luggage, 0.4320. Okay, so that's my good enough value for 10 iterations of this infinite sum. And I now have, so sanity check, right? Sanity check. We're going to look at this and we're going to look at this and realize at this spot, we're a little bit less than zero point 0.5 and quite a bit more than 0.25, and 0.432 actually fits the bill perfectly, right? So that actually makes physical intuitive sense, that the temperature at that spot, at least the theta, the dimensionless temperature at that spot, is 0.4320, right? So that makes sense. Okay, now I've got to convert this back into a temperature, right? Theta is wonderful for conserving chalk, but not particularly good if you actually need to report a real temperature. So remember, what do we do, right? We just define theta as the temperature at the spot we were interested in minus T1 divided by T2 minus T1. Well, look, hey, I know T1 and I know T2, so I'm just going to take the value of theta that I found from doing my infinite series. I'm going to plug it in here. And now I have one equation, one unknown. The thing I don't know is Txy. So I'm going to solve for Txy, which is what I'm doing right here, right? So here's my theta. Here's the T that I'm solving for. Here's T1, T2, T1 all over again. And so the actual temperature for this spot 0.5 X, 1.5 Y, is 343.2 Kelvin. And this is an example that I got from another book. And lo and behold, it checks out. And then I also ran this through AI, and it also gave me a similar answer. So green check, right? So I've got my temperature at that spot. Okay. So that's how you solve a infinite series with the exact solution. Pretty cool. Okay, let's move on. So this is an infinite series. When do you stop, right? All of you OCD engineers out there, you know who you are, right? You're like, wait. I just need to do one more. Oh, let's do n equals 12. Let's do 13. Let's do 14. Let's do 100, 200, 300, right? At some point, you got to stop. So when do you stop? Because they're diminishing returns, right? You don't have infinite computational power. You don't have infinite time. So you have to figure out when you're going to stop. So yes, fine. Theta of xy is a convergent series, but the terms diminish for higher values of n. So you're getting less and less and less benefit the higher and higher and higher up in n you go. So in textbook problems, they'll usually tell you the number of iterations that they want you to carry out. And the reason for that is because some automated grading system needs to check your answer. And so, you go long enough that you get an answer that's close enough, and the automated grading system says, that's awesome, check. For manual calculation, right, it's sort of up to you as the engineer solving the problem. But you typically will take the first 10 terms, for example, noting that all of the even values of n give you 0, at least for this formulation. And so really you're just taking the first 5 terms that have some non-zero numerical value. That's pretty standard if you're solving this by hand, right? And come on, guys, I'm old, right? Like back in my day when we used to walk uphill in the snow both ways to school, we did all this by hand because there was no other way to do it. So doing this 5 times is like painful, right? So that's kind of where you got a hand cramp and you had to stop is after 5 iterations. So that's where that comes from, right? We'll call that the law of conservation of hand cramps. Okay. So what did I say here? In open-ended problems, okay. Engineer must decide how many iterations are actually needed. So this is up to you guys when you encounter this in the real world. The number of iterations is often based on the needed accuracy of the measurement instrument. So if you think about something like a thermistor or a thermocouple, right? Like depending on how you've set it up and how you've calibrated it, you could probably measure maybe to 1/10 of a degree, maybe 100th of a degree if you're in a really ideal situation. And that's it, right? You can't get any better than that with your measurement instruments. So there's no reason to carry out these iterations any farther than your ability to actually measure that temperature, because who cares at that point, right? The instrument can't actually detect the difference between 0.001 and 0.002 Celsius, right? So just stop when you run out of precision decimal places in your instrument. I think that's actually the quiz question. First question is asking you when you stop, and that's the answer: is stop when you run out of ability to actually measure the difference between additional contributions from higher n values. So I say here, once terms diminish below this threshold, iteration stops, right? So, and the book, by the way, doesn't say that, right? The book is just like keep going forever, right? Like just, you're gonna die solving this problem. No, no, no. Like just stop when you like basically run out of instrument sensitivity. Okay, so that was fun. I love the exact solution. I think it's so cool and interesting that the exact solution exists, but then also it's an infinite series, right? It's like a real thing that you can write down, but you can never actually solve it. It's like incredible what heat transfer kind of spits out at us. Okay, so now we're going to transition, right? So let's go all the way back, all the way back, all the way back. Oh, right. Teach them while they're young. Okay, so we're going to go into approximate and graphical methods now. There's a kind of transitional type of solution, which is called a shape factor. So which is we'll talk about now as we transition. So what in the heck is a shape factor? Well, um, okay, we talked about like temperature profile on a flat plate. It turns out that there are other geometries that can be solved with exact solutions, and mathematicians are kind of nerdy and kind of bored, right? So they over time have solved a number of those different geometries and found the exact solutions, and they've just tabulated the solutions, right? Classic engineering, right? Let the mathematician do all the hard work and then just take all their results and put it in a table that you look up in a book, right? So that's basically what these shape factors are, is the exact solutions to slightly more complicated geometries that engineers probably don't have the mathematical chops to solve, from first principles, but we just steal from mathematicians because we're awesome that way. So I say here, rather than solving exactly from scratch, the existing solutions are tabulated as so-called shape factors. And the way that shape factors are formulated, right, it's basically just that same heat flux equation, heat transfer equation that we've always seen for conduction, except it gets modified by this thing called S, where S is the shape factor, right? So Q dot, which is a rate of heat transfer, is equal to S times K, the thermal conductivity of whatever it is that we're dealing with, times some temperature difference between two locations of interest. Right, so I say here, delta temperature is the temperature difference between a couple of the boundaries. And it just for, right, because we love that whole resistance thing, right? Where everything is a resistance model. Remember that from conduction. 1D conduction. So you can also write a 2D shape factor conduction resistance. And if you remember like the form of what resistance actually is, it's just like, 1 over this, right? Or delta T over Q, right? So here's our conduction resistance, right? It's just 1 over SK. So just in case you're doing a 1D conductive circuit and you have some two-dimensional feature in your otherwise one-dimensional geometry, and you need to represent that two-dimensional feature as a resistance in your one-dimensional model, this is what that resistance gets represented as. Okay, so what are these shape factors? So they're just all of these kind of arbitrary equations. Sorry, not arbitrary, right? This mathematician actually solved this. So they're exact solutions, but they just live in a table in the book. And a big part of this is kind of like pattern recognition, right? So you're given a problem and it's like, hey, that looks an awful lot like, shape factor number 7. And you just have to kind of match the geometry that you're given to the appropriate shape factor in the table in the book. You'll see in a second. So this is just one case to kind of give you a sense of what these look like, right? So this is an isothermal sphere buried in a semi-infinite medium, and the sphere is at some temperature T1, and the semi-infinite medium is has a surface temperature of T2. T1 and T2 are different from each other. And this buried sphere, buried in the semi-infinite medium, is basically transferring heat or absorbing heat, depending on whether T1 or T2 is hotter, from the semi-infinite medium. It's buried a distance Z into the medium. It has a diameter of D. And this is, just one example. I, basically buried a hot baseball in the ground, and I'm trying to figure out how much heat the baseball is conducting to the ground. And this is that, example. Okay, so two things to be aware of. One is restrictions, right? So mathematically, you have to check the restrictions to make sure that your particular configuration is compliant with the rules. And the rules are different for every configuration. In this case, Z, which is the burial depth, has to be greater than d over 2, which is the radius, right? Diameter squared, or diameter over 2 of this buried sphere, right? So provided that is true, this solution will give you a very good, if not exact, approximation for the heat transfer between this buried sphere and the top surface of whatever the semi-infinite medium is that the sphere is buried in. Right, so check the restrictions first to make sure that you're compliant. The other thing, the more important thing, or should say the equally important thing, there we go, is the actual equation for the shape factor itself. What is this S thing? So for this case, it happens to be 2 pi d over the quantity 1 minus d divided by 4z, right? And so presumably you'd be given the depth that this thing is buried, z, you'd be given its diameter, d. You would check the restrictions to make sure that you can use this shape factor in that situation. And then you'd plug in the given D and the given Z. Presumably, you know the temperature of this buried sphere and the temperature of the surface. And so now you could plug in a known value for S, a given thermal conductivity value, that temperature difference, and figure out the heat transfer rate between the buried sphere and the surface. That's essentially how this works. Okay. Um, Lots and lots and lots of shape factors, and there's many more that are even beyond what's in this book. In a world of AI, an expectation is that you should be able to basically find any shape factor for any kind of common geometry, right? So we're not going to be constrained to just what's in the book, because you can go out and search for other shape factors. So don't if you encounter a problem on a quiz, let's say, and you look through the book and you find that the geometry that's given is not any of these shape factors that's given in the book, that does not mean that it cannot be solved. That means that I am just challenging you to find the shape factor out in the literature, out on the internet with the help of AI, that will solve that particular problem with that particular geometry. So this actually, in a world of AI, is way easier than it used to be, because it used to be everything was tabulated in a book, right? Was we used to walk uphill in the snow both ways when I was a kid. You would always have to find shape factors tabulated in books. You have to like dig through pages and pages and pages and pages and pages of shape factors to find one that fit your geometry. And now you just search for it, right? So it's like a miracle. Okay, here's the ones in the book, and let me just give you some real world examples of where you might use these different shape factors, just to give you a sense, right? So we already talked about the isothermal sphere. That's case number one. So this could be like a thermistor bead embedded inside epoxy near a circuit board, right? So you've got a circuit board up here. You powder the circuit board in epoxy to do some either thermal management or intellectual property protection. You've got a thermistor that you've embedded in the epoxy because you're interested in measuring the temperature of the board so the board doesn't get hot and overheat. And that is this geometry, right? So you could use this shape factor to solve for the heat transfer between the circuit board, which is, dissipating heat because it's doing calculations, and the thermistor, which is measuring the temperature, by using this particular shape factor. So that's one. Case number two is a horizontal isothermal cylinder of length L buried in a semi-infinite medium, right? So this is basically like a hot water pipe buried in the ground, right? So hot water is being carried through this pipe. The ground is presumably colder. How much heat is transferring between the pipe and the surface? That's this shape factor. Next one, case number three, vertical cylinder in a semi-infinite medium, right? So you've got a cylinder, you jam it into the semi-infinite medium. The cylinder is at one temperature. The surface of the semi-infinite medium is at another temperature. How much heat transfer do you get in between those two? This could be, for example, a stake or rod driven into soil, right? So um, like a tent stake or something like that. And actually, interestingly, 1,000 years ago, I wrote a paper on trying to keep solar panels cold by like thermally anchoring them to the ground. And I use this shape factor as like my heat transfer calculation for how much heat a solar panel staked to the ground would be able to actually dissipate through into the ground through the stake, right? So, it's pretty cool. Here's the shape factor for that one. This next one, case number 4, is conduction between two cylinders of length L in an infinite medium. So we have two infinite cylinders that are basically communicating thermally with each other. So you can imagine conduction between adjacent, cylinders. Huh. Okay. I'm going to fix this one too. 11. Thermocouple beads are not cylinders. Conduction between adjacent thermocouple beads. I don't know where that came from. I must have imagined late at night in my sleep deprived state that these were spheres. Okay, so this is just like two pipes, right, that are running parallel to each other. One is hot and one is cold, and they're basically conducting heat from the hot to the cold through a semi-infinite medium that separates them. So I'll fix that when we finalize the slide. So here's a shape factor for that one. Case number 5, horizontal circular cylinder of length L midway between parallel plates of equal length and infinite width. So this one, right, you've got this cylinder and it's between kind of two um, uh, surfaces of constant temperature. And that looks an awful lot like a cartridge heater embedded in the center of a mold or a die block. Right. So if you were like heating up something that then is encased in a mold or a die block, this is the shape factor for that one. And I can go on and on and on and on. Case number 6 is circular cylinder of length L centered in a square solid of equal length. So this looks an awful lot like an electrical resistor dissipating heat inside an enclosure, right? Super useful for mechanical engineers. You guys like put electronics in boxes all the time, and then you're like, bro, I don't know how much heat is being transferred between my electronics and my enclosure. Here's how you do it, right? I just solved all of EML4502 for you guys. That's the shape factor for that situation. Um, Case number 7, eccentric circular cylinder of length L in a cylinder of equal length. So, right, I've got like a cable running through a conduit. The cable has electricity running through it, so it's dissipating heat. It's at constant temperature. And how much heat transfer am I getting between this power carrying wire and the outside conduit, right? That actually happens all the time as you're pulling power cable or pulling communication cable through a conduit. You get kind of an off-center configuration like this. So that's a very common one. Case number 8, conduction through an edge of adjoining walls, right? So imagine like a refrigerator cabinet that has to stay cold, right? You could do 1D heat transfer on all of the surfaces, right? But on the edges, you have this confluence of two different surfaces, and that confluence is a two-dimensional object, right? So you've got to do 2D heat transfer. So here's the shape factor for that one. And then here's a three-dimensional version of it, right? So instead of an edge, this is a corner. So a corner of an insulated electronics enclosure, right? And here's the shape factor for that one. Case number 10, this one I love. Disk diameter D on a semi-infinite medium of thermal conductivity K and temperature T2. Um, do not try this at home, kids, but this is, imagine your finger pushing down on a hot surface, right? Your finger makes basically a conical uh, circular shape, and it's at whatever your skin temperature happens to be. And then here's the underlying hot surface. So um, don't try this at home. Please don't put your finger on a hot plate to test this. But you could actually figure out like how much heat gets transferred from a hot plate to your finger with the shape factor if you touch like a stove, right, or a hot pan. That's I think pretty cool. Okay, and then there is a square channel of length L. Um, so we have a channel that has an internal temperature and an external temperature. It's basically um, um, like an annulus, except in a square shape. And so that's like an internal cooling channel inside a rocket engine wall, right? So if you guys have ever like taken a slice of a rocket engine or a slice of a fin in a gas turbine, they have these tiny square channels. They run gas through the inside to try to keep things cool. You know the surface temperature because you know the temperature of the gas that you're introducing. You know the outside temperature because that's the products of combustion from your rocket motor. And now you guys have the shape factors to figure out what that heat transfer rate is, right? So yeah, you're welcome. You're welcome, Rocket Lab guys. You're welcome. All right. Um, there's more. Case 12, case 13, case 14, case 15. These are a little bit different because instead of heat transfer from one object to another object at two given temperatures, these are heat transfer from an object to an infinite medium at a particular temperature. So the challenge with these is that there's no characteristic length, right? In all of these cases, there's some characteristic length, characteristic distance between the sphere and the surface, the cylinder and the surface, right? The depth of the semi-infinite, or sorry, the depth of the cylinder. There's the distance between these two cylinders. There's always some characteristic length. Now that you have an object all by itself, there's no characteristic length, and so we need to calculate a characteristic length and then plug that into an equation that's specifically set up to kind of deal with or process the characteristic length. So we'll get to the characteristic length in a second. Let's just talk through these examples. So we have a isothermal sphere of diameter d and temperature T1 and a semi-infinite medium of T2, right? So here's our sphere, it's buried. So cool example of this would be like a molten inclusion trapped inside metal casting, right? So you melt metal, you pour it into a mold, it solidifies, but then there's little hot spots, and those little hot spots are transferring heat to the solidified metal following this shape factor. Infinitely thin isothermal disk at temperature T1 inside a semi-medium of T2. So this could be, for example, a thin circular explosive initiator embedded in a solid rocket propellant grain, right? So if you guys are doing rockets and you're interested in like, what temperature does this have to get to facilitate combustion in your solid rocket motor? Now you've got a shape factor for that, right? This one is an infinitely thin rectangle in a semi-infinite medium. So this looks an awful lot like a copper trace on a printed circuit board embedded in resin, right? So if you've ever made a PCB, all those little traces of copper, right? And then you coat over them with resin to protect them or provide IP protection or heat dissipation, right? So you just now treat the dimensions of that copper trace using L and W, and now you have a shape factor for how much heat is transferred from this thing as it's carrying current to the resin that's protecting it. Or a cuboid of height D with a square footprint at temperature T1, conducting into a semi-infinite medium of temperature T2, or say infinite medium of temperature T2. This is like a sensor package embedded in concrete that you're actually powering, right? So it's dissipating power. So imagine you're trying to, measure the temperature of a bridge or something like that, a building, and you've got a little sensor pack that you've actually intentionally embedded in the concrete so that you could take constant measurements of the temperature of that structure. Now you have a shape factor for that, right? So yeah, you're welcome. Okay, so I say here, dimensionless conduction, heat rates, model conduction from an isothermal object T1 embedded in an infinite medium of uniform temperature T2. That's all of these kind of weird characteristic length cases. Useful results are obtained by defining a characteristic length, as I described before, which is ultimately defined by the object's surface area. So, how do we get to an actual equation that's useful? What we're interested in is Q dot. To get to Q dot, we figure out the appropriate geometry. We use the right shape factor, right? So 1 square root of 2 times 2 over pi, 0.2 or 0.932, etc. That's the Q star SS value that goes in here. Multiplied by K, which is the thermal conductivity of the infinite medium, multiplied by AS, which is the surface area of the object um, embedded in the infinite medium. T1 minus T2, that's the temperature difference between the buried object, the immersed object, and the surrounding environment, and then divided by L sub C. We calculate L sub C, that's our characteristic length, by just taking the surface area, dividing by 4 pi, taking the whole thing to the 1/2 power, so it has units of length. That goes in here, and now this becomes our equation for heat transfer, right? But the shape factor is now this Q star SS thing instead of just S. Okay. Next, we're going to talk about finite difference, right? So if we go all the way back, all the way back, all the way back, remember, right. Get them while they're young. We've talked about exact solutions, approximate methods, and numerical methods is next. So here we go with numerical methods. Oh, too far. There we go. Okay. So there's this thing called the finite difference method. Let's just go through these bullet points. So 2D problems often involve geometries or boundary conditions that preclude exact or tabulated solutions, right? So unless you have a really simple geometry like a flat plate or a sphere or a square or something like that, you probably aren't going to be able to find an exact solution, and you might not be able to find a shape factor if you've got some customized geometry. So what do you do in that case? Well, as I say here, the best alternative is a numerical technique, and there are several, finite element, finite difference, boundary element, and so forth. Numerical methods can be extended to even three-dimensional problems. We've been talking about 2D here. We're going to stay with 2D, but if you wanted to, you could actually, solve a third dimension, which of course gets more mathematically complicated, more computationally intense, but still solvable. The trick with numerical solutions, as I've been kind of harping on this whole time, is that you can only determine temperatures at discrete points. And we'll talk about kind of how those points emerge from a technique called meshing in a couple of slides. But oftentimes that's good enough, right? You maybe are interested in the temperature here, but temperature here is close enough, right? So maybe that's okay. Or you could reduce the size of the mesh and get to the temperature at the spot that you're interested in, but with more computational power. So we're going to end up taking an object of interest whose temperature field we are interested in finding, and we're going to subdivide it into numerous smaller regions. And each one of those smaller regions is a reference point called a nodal point, and that nodal point exists at the center. And so what ends up happening is you take this object and you cover it with what's called a mesh or a grid or a nodal network. So those terms are used kind of interchangeably. And then as we'll see in the next slide, as I zoom in on this node, notice I have an x-axis where the continuous axis is x and the discrete axis is m, right? So m is going to start here counting from 0, and this is going to be 1, 2, 3, 4, 5, and so forth. And then y is the same story, right? So y is continuous, but n is discrete. And if I start counting from here, I'm going to have n equals 0, 1, 2, 3, 4, 5, and so forth. And so using that kind of discrete n and m coordinate system, you can identify each one of these node points, which, by the way, are all separated by delta x or delta y, right? The same distance. It doesn't have to be the same distance, but usually, at least for simple solutions like we're going to talk about, it's the same distance in the x direction and the y direction. And then each one of these separations is always the same distance in both directions. Every time one of those distances is traversed and it's crossed by both a delta x and a delta y, you end up with this spot, right? And then I'm going to take this and I'm going to kind of zoom in, and that spot is m comma n, right? So m, again, is the number of steps that you've taken in the x direction, and n is the number of steps you've taken in the y direction. And lo and behold, if I have a spot, which I'm going to call mn, I can go up 1 in the y direction, and that's mn plus 1. I can go down 1 in the y direction, and that's mn minus 1. I can go to the right in the x direction, that's m plus 1n, or I can go left in the x direction, and that's m minus 1 n, right? So you can basically use this mn coordinate system to navigate your way around all of these nodes, and those nodes, as we'll see in a second, become important because those are the spots where you are actually calculating the temperature. Okay, let's dig more into the finite difference method. So each node represents the surrounding region. The node temperature is the average temperature of the region, right? It's not an exact temperature at that spot. It's the average temperature of the region that it represents, right? Think of it sort of like as a capital city, right? Gainesville is the capital city of Alachua County. And so whatever the temperature is of Gainesville is representative of the average temperature of the entire county. Presumably the city's right in the middle. So the numerical accuracy depends strongly on the number of nodes. So the more nodes you have, let's go back, the more nodes you have, the more spatial accuracy you can get, but also you have to have more equations to solve simultaneously, which requires more computation, right? So you can make the nodes arbitrarily small, but then you have to wait an arbitrarily long time for your computer to actually solve all of the simultaneous equations that get produced. We'll see that in a second. So in order to create those equations, we need to solve the appropriate energy conservation equation for each node of unknown temperature. And then we're going to use those resulting equations. We're going to solve them simultaneously, and that's going to give us the temperature of the node. This, by the way, is why we had you take linear algebra, because there's a lot of linear algebra in finite difference solutions. Okay, so what are we really doing? Well, remember, if I go all the way back, get them while they're young. I'm basically solving Poisson's equation in 2 dimensions, right? This is the equation that I'm solving. This is not an exact solution anymore. It's an approximation, but I want to start from kind of the foundations of I am solving this problem. So if we cruise forward here through shape factors back to this, if I'm taking the second derivative of temperature with respect to x, at some spot mn, what am I actually doing? Well, I'm taking the difference between the derivative one step to the, or I should say 1/2 step to the right, minus the derivative with respect to x of 1/2 step to the left, right? So that's what m plus 1/2 and m minus 1/2 means. I'm basically just looking at that spot and that spot, right? Because that's 1/2 step. If a full step from m to m minus 1 is moving from one node to another, half of that gets me right there and right there, which is representative of the edges of this region where the temperature of my node is representative of the average temperature of that region. And then because I'm taking a derivative, right, I'm dividing by delta x. And notice, right, these are still partial derivatives with respect to x, but then I have to define those partial derivatives with respect to x also in terms of my nodal network, right? So this term, dt dx at m plus 1/2 comma n, is a first derivative with respect to x, and I can approximate that as a difference between the temperature here, the temperature here and the temperature here divided by the distance, right? It's an approximation. I'm taking, basically a step from one spot to the other, dividing by x, and that's representative of my derivative. The same is true in the other direction, right? So I'm taking the temperature here, I'm subtracting out the temperature here, right? mn minus 1 comma n, temperature there, and I'm dividing by x, and that's representative of my derivative from this spot to that spot, right? Not exact, but a linear kind of approximation to those exact derivatives. So I've now got this expression, which is a difference of derivatives divided by delta x, and then I've got the expression for the approximation to the derivatives themselves. So I can take all of this, I can write out now an approximation for second derivative of t with respect to x at my spot mn. I can also write out an approximation for my second derivative temperature with respect to y at that spot mn. And notice all I'm doing is just adding up, right? Just adding up these sums and differences. And this is what I get for the X direction, and this is what I get for the Y direction. And so now I'm going to take those two expressions, which again are my kind of linear difference approximations for these derivatives, and I'm going to plug them back into my original Poisson's equation, right? This is what we're ultimately solving for. And what pops out is this expression, right? I'm just adding up all of these temperatures, right? And then what comes out of it is the temperature that I'm actually interested in, right? TMN. That's the temperature at the center, at the spot of center spot of my region. That's minus 4 MN. And so if I know this temperature, this temperature, this temperature, and this temperature, I could solve for TMN, right? By just dividing everything by 4. So what do I say here? I say for the MN node, so that's the node that I'm interested in that's kind of in the middle of my field of view. The exact heat equation is reduced to an approximate algebraic expression, which is this. And this finite difference heat equation is applied to any interior node equidistant from 4 neighboring nodes, right? So these are all delta X or delta Y away from each other. Typically, delta X and delta Y are the same distance, right? So we're talking about square nodes. It doesn't have to be that way, but the math is a lot easier if it stays that way. And so we're basically just now taking average temperatures. So we take temperature here, temperature here, temperature here, temperature here, take the average of that. That gives us the temperature here, which is the temperature of this region, right? So that's essentially what we're doing. It's just taking averages. Okay, so this can now get a little bit more complicated, right? Whereas before, when we were solving this guy, remember we said that heat generation had to be 0 to get us the exact solution to Poisson's equation. Well, now we can get a little bit more complicated because we're no longer solving these complex, horrible differential equations. We're now just basically, summing up averages, right? So if I had a node that had its own internal heat generation, I can add that, right? And I can actually solve for that heat generation. So I say here, we can extend the finite element method using so-called energy balance method to analyze problems involving multiple materials, embedded heat sources, exposed surfaces, or even geometries that are not aligned with the coordinate axis system. So the one we're going to talk about here is embedded heat sources, but you can use this for all of these. So we're going to apply conservation of energy to the control volume about the node. In order to make the math work out in a way that's sensible, we're going to assume something that's going to feel kind of icky because it's impossible, which is that we're going to force all the heat flow into the control volume, right? So what does that mean? That means that if I look at like the 4 surrounding nodes, I'm going to write the equation with the underlying assumption that each one of these is delivering heat from itself to this central node. And of course, that if you think about from a thermodynamic perspective, that should feel very icky because what that means is that this temperature is going to keep increasing and increasing and increasing, where we know that we're actually solving for a steady state situation. Where the temperature cannot just increase indefinitely. So you'll see it'll resolve itself, right? We're basically just choosing a sign convention, and what will end up popping out of this sign convention is some of these heat fluxes will end up negative, right? They'll go in the opposite direction to what we've chosen, right? But for now, we're going to just treat them all as heat in. And of course, if you remember from thermo, heat in is always positive. So we're going to have all 4 of these coming in. So here is my first law of thermodynamics for this node, right? Here's my control volume surrounded by my dotted control surface. I have 4 heat fluxes entering, and I have, remember, we're solving this for heat generation. Where is heat generation? Embedded heat sources, right? So heat generation. And so if I write the first law of thermodynamics in steady state, here's my first law in all of its glory. And then I'm going to cross out the time derivative term because we're in steady state. I'm going to leave the energy flux into my node, right? Because that's these 4 energy fluxes. So that cannot be 0. I'm going to uh, get rid of E out because there's no energy leaving, right? Even though we know in reality there is, we're going to treat it as if no energy is leaving. And then we're going to leave this generation term in there in case we've got generation inside this node. And so what we end up with from the first law of thermodynamics is this equation, which is basically the energy flux in plus the energy generated inside the node is equal to 0. And in order to find the energy in, well, the energy in is just the heat flux through conduction from node 1, node 2, node 3, and node 4 surrounding my internal node. And so I'm just going to write this as the summation from I equals 1 to 4 of those 4 heat fluxes from node 1 to node Mn, and then node 2 to node Mn, node 3 to Mn, and 4 to Mn, right? That's what this represents. It's basically E dot N, but for each of the 4 surrounding regions, transferring heat through conduction into my central region, which is whose temperature is represented by this node at Mn. Okay, and then here's my heat generation term, right? So here I've got heat generation, and of course this is heat generation. I should probably make this per unit volume. So I'm gonna make a little note, and when I post this slide, this Q dot is gonna have a triple prime sitting behind it. So you know it's heat per unit volume. And then I'm going to multiply by a volume. What volume? Well, it's the volume of the node, right? So this node is delta X wide and delta Y tall. And remember, into the page, it doesn't matter. So I'm just going to call it unit 1 into the page because this is a flat object. And so that's my volume. My volume multiplied by my volumetric heat flux gives me my heat generation. And I just added these two together and set them equal to 0 because that's what my first law says. And so this equation is basically just a more sophisticated version of the first law of thermodynamics set up for my nodal finite difference analysis. Okay. So we've got this equation. So now hopefully you understand what the equation means. And then we are going to just apply Fourier's law of conduction from each one of these surrounding nodes to the central node whose temperature I'm trying to solve for. And notice that heat flux through Fourier's law of conduction traverses through an area of, let's just look at this node, right? So m minus 1 m n. This distance is delta y, and then the distance into the page is, doesn't matter, so we'll just call it 1, right? So just a unit distance into the page. And that gives us an area, right? We can only see like the top of the square or the rectangular area that's created, but there is actually an area that's facilitating heat flux from node n m minus 1n to mn. So that's this area. Okay, so what is this heat flux then for that particular node? It's the heat flux from m minus 1 comma n into mn is equal to the conductivity of whatever this material is times the area that the heat is being transferred across times the temperature difference from this spot to this spot, divided by the distance that the heat travels from this spot to this spot, which of course is delta X, right? It's each one of these blocks is delta X wide. And so if we take the center to the center of one of these blocks, that distance is delta X. Okay, so I say here, this is the finite difference approximation to the temperature gradient at the boundary between the nodes, right? So that's what this thing in the brackets is, finite difference approximation to the temperature gradient at the boundary between the nodes, right? Think of this as, let's see, did I write it here? No. Think of this as, yeah, these derivatives, right? It's just a temperature difference divided by a spatial distance difference. It's a derivative with respect to x or y. Okay. So I've written this now for this node transferring heat via conduction to this central node. I now need to write the same expression for the top node, the right node, and the bottom node. So here I am doing that, right? I'm just writing it in every case. Notice when I've got nodes that are above and below, the heat transfer area is delta X, times 1 instead of delta y times 1, but then the distance that I'm stepping from the node on the edge to the node in the center is delta y instead of delta x. So those two things basically like switch positions, and we'll see when we go through the derivation, all of that cancels out, right? We're basically going to cancel out all the delta y, delta x's. And so, but it's important to know that because we're like switching indices from the x and the y direction, those two things do trade places. So just be aware of that in the math. Okay, so then I say here we're going to subtract Mn node temperature from the adjoining node temperature, and the convention. Oh, okay. This is what I was saying before. This convention is necessitated by the impossible heat flow towards Mn, right, that we assumed before, but still consistent with the flow direction. And what we'll see in the next step, you'll see it in a second, is because we made this assumption that all of the heat is traveling from each of these nodes to the center, we don't have to keep track of like what's positive, what's negative, what's in, what's out. We just assume that everything is coming in, and then the numbers will work out on their own, right? The directionality of where the heat is going will work out on its own, provided we stick with the same convention. So just wanted to point that out, that the reason that we did this is to make the math really simple, right? We end up with basically the same expression just repeated 4 times. And again, the signs will work themselves out in the next step. Okay, so I now have this expression that comes from the first law of thermodynamics for my central node. I have expressions for the conductive heat transfer from each of these adjoining satellite nodes into the central node. We know that the nodes are the same delta x and delta y, right? They're the same size. And so what ends up happening when we put all of these expressions into this equation is we end up with something that looks very similar to my finite difference equation, with the exception of this extra heat flux term, right? So this is that extra term that accounts for the generation, but otherwise it's identical. So there's actually an example later on where I solve this, so you'll see how this works. But all you would need to know in this case is what the heat flux per unit volume is, what the step size is, the distance from one node to the next, what the thermal conductivity of the material is. You plug in those values to get this term, which represents the heat generation in this node. And then you just plug in the temperatures of the 4 surrounding nodes, and out pops the temperature of the central node, right? So it's basically the same thing we were doing before with just one extra term. Not too bad. Okay, now things are going to get a little weirder, right? A little worse. We're going to take the energy balance method. We're going to extend it one step further to a situation where we're dealing with edges, right? So I say here, need a finite difference equation for each node where the temperature is unknown. So every place that you don't know the temperature, you need an appropriate equation like this one or this one to solve for that unknown temperature. But what happens if you're not an interior point, right? If you're sitting on an edge and you have some non-conductive boundary condition that you are exchanging heat with the ambient environment, for example, through convection. So I say here, for non-interior points in contact with either an insulated surface or exposed convection, we want to obtain a finite difference equation via an energy balance, right? So we're going to go all the way back to our first law of thermodynamics, and we're going to write an appropriate energy balance. And I'm just going to show you an example using this particular 3/4 shaded node. This node is a surface node. It's in a corner, and it's conducting heat with the 3 nodes that are surrounding it on the left, the top, and the right, but it is convecting heat to or from the ambient environment at some ambient temperature with some convection coefficient, right? So we have a convective heat transfer boundary at this corner, and then we have a conductive heat transfer boundary all the way around the outside of the object. And it's kind of a misnomer because it's actually the inside of the object, right? It's the inside of the solid object that's conducting to and from the surrounding nodes. Okay, so we are going to have the same equations as before for conduction coming across this surface, right, which is a full surface, and conduction across this surface, which is a full surface. So we see here Q of m minus 1n, m minus 1n going in, right? That's just our old conduction equation from before when we had heat generation. And this one, m n plus 1, m n plus 1. So that's conduction across this surface, which again is the same, the same equation as we had before. We need two new equations now for the convection on this surface and this surface. So here's that expression, right? So I have, so let's just look at what's going on across this kind of corner, right? So I have half of that corner experiencing conduction, and then I have the other half of that corner experiencing convection. So here is my, right? So here's yeah, here's the node right here, mn minus 1 to mn, right? So here's mn minus 1 to mn. So here is the conduction part, which is just the same as before, except the area that the heat is traversing through is half of the total area. Why? Because there's only half of the area there, right? This is air. This is the solid, this is the air. So that's where this 1/2 comes from. And then the other surface, this surface, is going to be experiencing convective heat transfer, right? And it's going to be experiencing convective heat transfer over a distance of delta x over 2, half the total distance of the object, multiplied by 1, depth into the page, and then times the temperature difference between the ambient air blowing past and whatever the temperature of that node is, right? So that's this term. So if I add this term, which again is the heat flux through this surface, and this term, which is the heat flux through that surface, now I've got an expression for the total heat flux for node m n minus 1 into node m. And I'm going to repeat it again for node m plus 1n, this one, into node mn. That's this expression, which has a convective component and a conductive component for the same reason as we just discussed. So now I have a complete set of equations to go into my original first law energy balance. I've got my two purely conductive pathways, right, across this surface and this surface. And then I have my kind of hybrid pathways that have a convective component and a conductive component across this surface and this surface, and then also this surface and this surface, right? So that's these two. I'm going to do what I did before. I'm going to just take them and stick them into this equation. Everything adds up, and terms condense, terms coalesce, and what I end up with is this expression, right? So got this guy. You can recognize, right, here's that 1/2 that came from here, and here's the convective coefficient that came from here. And instead of 4, I've got 3 plus a convective boundary right here. So same equation with just a few subtle changes. But if I know the temperature at these surrounding nodes, m n minus 1, m minus 1n, m n plus 1, and m plus 1n, and I know the thermal conductivity of the object, and I know the convection coefficient, I can plug in, and I know the infinite ambient temperature, I can plug in to get this value, I can plug in to get this value, and now it's just like before, right? Just like we did before. I know this temperature, this temperature, this temperature, this temperature, and I'm solving for this temperature, right? So just the way we did it before, with just a couple of extra terms that now account for a convective heat transfer coefficient instead of a conductive one, right? So no big deal. Okay. There are all kinds of different boundary conditions that you need to worry about. So you need to worry about internal corners. You need to worry about kind of external edges. You need to worry about external corners. You need to worry about, those are all convection. These are all now constant heat flux. And so we have this whole set of cases that give you the appropriate equation for the interior node, the node at an internal corner, the node along a plane surface with convection, a node at an external corner with convection, and a node at a plane surface with uniform heat flux, right? So, okay. And then I just say here, finite difference equation for an adiabatic surface or surface symmetry can be achieved by setting H or Q double prime equal to 0, right? So if you have an adiabatic surface here, instead of a forced convection heat transfer coefficient, you just set, oops, okay. You just set H equal to 0, right? Just H equal to 0. There's no heat transfer across that surface because presumably it's insulated. And this equation will still work for you to get the correct TMN for that particular node if it's now sitting in a corner that's insulated instead of exposed to forced or natural convection. Okay. Okay. Cool. So, one more finite difference energy balance with thermal resistance. So I say here, heat rates between adjoining nodes can also be formulated as thermal resistances. So again, just like when we were talking about shape factors, and I talked about this expression, right, for the conductive resistance in the context of a shape factor. We can also do it for finite, where is it? There it is. For finite differences. So I say consider the heat transfer by conduction from node m minus 1m to node mn. And so this is that equation. And this is that conduction that we need to find. But I already know what this equation looks like, right? From the equations that are provided, right? So like any of these equations, like this one, right? So I know what this equation looks like, right? There's a K, there's a delta Y, there's a 1. And so all I need to do is compare this to this form of the equation, right? My kind of classic Q equals delta T over R, and figure out what R is, what the resistance is. So in this case, the resistance is just delta X over K times delta Y times 1, right? So I can just take that and plug it in, and that's my conduction resistance. Okay, so kind of a similar idea, but now we're just going to be dealing with thermal contact resistance. We can write an equivalent thermal circuit for two nodes made of dissimilar materials that have a contact resistance that's known, that's tabulated by using this resistance representation that I showed up here at the top of the slide to write the appropriate heat transfer equation with a total resistance that includes both a contact resistance and a resistance for heat transfer between the material where the node is sitting, right? So I say here, consider an interface separating two dissimilar materials characterized by thermal contact resistance R double prime T comma C, T for thermal, C for contact. The heat transfer rate from node Mn to N minus 1N is expressed as, right? So here it is. So I've got my two nodes. I've got this node, I guess, transferring heat to this node. Yep, that's what this arrow implies. And so it's just this temperature minus this temperature divided by whatever resistance exists between them. What is that resistance? Well, it's the resistance of this part of the path, right, which is here, right? So delta y over 2, right? The total distance is delta y, so I'm traveling delta y over 2. Divided by Ka. Ka is the thermal conductivity of material A, and then multiplied by the cross-sectional area that heat transfers, which is delta X, right, times 1, which is the distance into the page, which again, we don't care about, so we just use a unit length. Here is the actual contact resistance. So that's a value that will be given, and then that gets divided by the area across which the contact resistance is acting. And then we're going to add another thermal resistance from this spot down to my central node. And what is that? It's just, again, half the distance across an entire one of these regions, because that's the distance that the heat travels from this interface to the node, y over 2, divided by KB, which is the thermal conductivity of material B, and then divided by the cross-sectional area across which the heat traverses, which is, in this case, delta X multiplied by 1, where 1 is the length of the page. Okay, so I think we've, pretty well beaten that into the ground. So now that you have all of these different equations and you know how to write them and you know how to kind of deal with all these edge cases, how do we solve these equations? Because remember, the ultimate goal is to get back to a temperature field, right? Temperature of X and Y, or temperature of M and N, so that we can then determine heat fluxes. So I say here, solving finite difference equations. Once the nodal network is established and appropriate finite difference equations are written for each node, the temperature distribution, which is our goal, can be determined by solving a system of linear equations, right? So you end up with all these equations, all unknowns, not all unknowns, all these equations that include all of these unknowns, and you have to solve them simultaneously. This, by the way, right, is why we had you take linear algebra, so that you could solve these things simultaneously. Okay, so how do you do that? There's multiple different ways. I will mention that a lot of like computer software packages will do this now, with not too much difficulty. But it's good to know the underlying mathematical like explanation for why things are the way they are, so that you can spot check if you've got a computer or an AI telling you that it's doing something. You can actually intelligently critique it, instead of just saying, yes, AI, you are right and I have no idea what I'm talking about or what I'm doing, right? So okay, so we're going to consider a system of n finite difference equations corresponding to n unknown temperatures. So this is just some object like this, right? It has a whole bunch of different nodes. I don't know the temperatures of any of those nodes, but I can write equations for each one of those nodes, like this equation, right, for the temperature of this node, and I can write them all simultaneously. I can even write an equation like this if I have external nodes, or I can write an equation like this if I have nodes that are represent a contact resistance between two dissimilar materials, right? So you have a lot of tools at your disposal to write these equations, but we got to write them. Okay, so then we're going to identify the nodes using a single integer subscript rather than the double subscript that I've been using up until now, right? So up until now, I've been talking about m comma n, and moving forward, we're going to drop the m comma n, and we're just going to um, represent it as 1 1 2 1 1 2 2 2, and so forth. Eventually, we're going to get up to n um, way down at the bottom right hand corner of our matrix, right? And that's where we're going. We're actually going to write these expressions. Right now, they're just a series of linear equations, but you've presumably taken linear algebra, and so you can write them with just the coefficients in matrix form and solve using all of your matrix math skills. So the quantities A11, A12, A13, A21, A22, and so forth, as well as C, are known coefficients that come from your equations, and they're constants involving the quantities delta X, K, H, and T infinity, right? So those are going to be constant values that don't change. We're going to try to represent this as matrix notation. So here is the A matrix, right, which just has all the constants in it. This is the T matrix, which is the temperatures of all the nodes. This is the one that we actually care about and are trying to solve for, right? So that one sits here and here. And then this is the C matrix. And I describe that, well, I describe that down here. So I say a coefficient matrix A is a n by n square with elements designated by double subscript notation. That's what I was talking about before. 1 1 1 2 1 n 2 1 2 2 n 1 N2, and so forth, right? So instead of M comma N, we're just using a two-digit number now to represent where these numbers exist inside this matrix. Okay, the first subscript is the row, the second subscript is the column. Hopefully that's self-evident. Um, and the matrices T and C, here's T and here's C. T is the temperature field, C is the solutions, are each a single column, right? So you can see where this is going. There are numerous numerical methods or mathematical methods available for solving systems of linear equations. And our goal is to find, given the solutions to our equations and this matrix of coefficients, mostly material properties, our goal is to find the matrix T, right? So to find all these values, which is the temperature field. Okay, so I say numerous mathematical methods are available for solving systems of linear equations for the solution vector T. Okay, so we're going to just talk about one of those solutions, right? Pretty powerful, drives fast convergence if the situation works out that the matrices are amenable to it. It's called the Gauss-Seidel method. And so our goal, again, is to solve for the T vector, the T matrix, to obtain all the finite difference node temperatures. Right, so we're basically trying to find the temperatures of all of these nodes by solving all these equations simultaneously. And then doing some very cool matrix manipulation to get the answer out. Okay, so let's walk through this Gauss-Seidel technique. So step one, if possible, we want to reorder the equations. When I say reorder, right, remember from linear algebra that you can switch the order of equations without, changing the solution, right? So I can just take the first line and make it the second line and so forth. So reorder the equations so that the diagonal elements with higher magnitudes are larger than all elements in the same row. So in the case of the first line, A11 is going to be the diagonal for matrix A. And so we want A11 to be bigger than A12 and A13 and A1C and all the way up to A1N. In the second row, A22 is on the diagonal. So we want A22 to be bigger than A21, A23, and so forth out to A2N. And then in the third row, it's going to be A33, and the fourth row, A44. We always want that diagonal to be the biggest number, if possible. The resulting system is called diagonally dominant. And the reason that we want to do this in the beginning is we want to set ourselves up for fast numerical conversion, right? You don't want your computer to be cranking away trying to solve differential equations all night. So convergence is driven faster and maximized. The number of iterations is minimized if we've got the biggest number in each equation actually sitting in that diagonal spot. So that's a good technique to just speed up your process. Doesn't change the answer, right? Because we're just switching the order of the rows in the matrix, but it will speed up your computation. Nonetheless, it is true that convergence is still possible, even if diagonal dominance is not obtained, but the process is slower, right? So if you've got the brain cycles and the bandwidth to reorder so that you've got the highest numbers on the diagonals, you will get a solution faster, right? That's all that is effectively saying. Okay, step two is we want to write each of the n equations in explicit form for the temperature represented by its diagonal element, right? So that's, and I'll give you guys an example, right? Because this is kind of mathematical gobbledygook, mathematical gibberish. So I'll explain what this means with an example, but we're basically writing an expression for each individual temperature in terms of all these different parameters. You'll see when we do the example. Okay, so step number three is the initial value, that's iteration 0, so k equals 0, is assumed for each temperature Ti, right? So we have to start by just guessing what the temperature field is across this entire object. We have no evidence for what it actually is. We're just going to guess values. Maybe you've, made an educated guess using an approximation technique. Maybe you have, um, cold soak the thing, something like that, so you know that it's at a particular temperature. But you have to guess at what that initial temperature field looks like. Um, the needed computations go down by selecting values that are rational estimates for the actual solution. So, the closer you get to the correct solution on your guess, the less computational power is required to drive the equations all in that direction. But again, an initial guess that's super accurate is not necessary. It just increases the amount of computation that you have to do in order to get to the solution. Okay, next step is we're going to set iteration k equals 1. Um, and then we're going to say values of t of sub I of k equals 1 are going to be calculated by substituting the assumed values from the previous step, right? K equals 0, second summation, k minus 1 equals 0, and the new first summation, k equals 1, and values of TJ are going to end up appearing in into the right hand. Oh yeah, sorry. TJ is right here, into the right side of the equation, right? So okay. So what are we doing? What is this? We've got like the current guess. We've got the previous guess. We're gonna plug all the values in here. We're gonna plug all the values in here, and out is going to pop a guess for temperature at a particular node for a particular iteration k. And then we're just going to continue doing that, right? Continue iterating by calculating new values of t sub j. This is not an exponent, right? This is just an indice that's counting how high we're going in k from the t sub j k values of the current iteration, with some parameters given for what j needs to be relative to I. Okay, probably easier to actually show you this as an example because this is sort of mathematically kind of gobbledygook. Two more things to notice in steps 4 and 5. So step 4 is basically setting the value for k equals 1 and plugging in all the values for t sub I at k equals 1, and then calculating the differences between the current iteration and the previous iteration, and then continuing to iterate on that process until you converge to viable temperatures. So I say since t sub I values for a particular iteration are calculated sequentially, each value can be computed using the most recent estimates of other TI values. The value of each unknown is updated as soon as possible. Okay, so what does that mean? That means this is a little bit different than the way that you probably solved the matrix before, right? You probably just written a series of linear equations and you've solved them all simultaneously and out pops the exact answers. This is not that approach. This basically uses the equations, you plug in a guess, you use the resulting values from the guess, and you plug them back into the original equations, and you do that over and over and over again until you get to convergence. What is convergence? Well, convergence is some preset criteria, epsilon, and you terminate the iteration process when that preset criteria is achieved. So basically when the temperature between the current iteration and the previous iteration for each node is small enough that its absolute value is less than some threshold that you set, which at least in this slide show is epsilon. So that's how you know when to stop this process, is when your temperature difference between the previous iteration and the current iteration is small enough that it meets whatever your criteria is. Okay, let's actually do this, right? Because it's a little nuanced. So I'm just going to write a simple series of equations. So I've got them here, right? So 4x plus y plus z equals 7, x plus 5y plus z equals minus 8, 2x plus 3y plus 10z equals 6. And you guys could solve this, right? I've got 3 equations and 3 unknowns, not too difficult. You guys could go through and actually solve independently for x and y and z, get those values. You know how to do that. So this is a good example because you know how to solve it in kind of a conventional way. So let's just see the Gauss-Seidel approach and see how that changes things. So we're gonna rewrite this in matrix form, right? So remember our preferred matrix form is A times T is equal to C. Each one of those is a matrix or a vector. Here's the A vector, here's the T vector, which we'll call T, X, Y, and Z. And then here's the C vector. Where do all these things come from? Well, look, 1, 1, 1, 1, 1, 1, 1, 5, 1, 1, 5, 1, 2, 3, 10, 2, 3, 10, 7, minus 8, 6, 7, minus 8, 6. So these numbers actually get pulled right from the combination of linear equations that you're using to try to solve for x and y and z, right? So that's where these come from. Notice, and this is the solutions, right? That's where these come from, is the column of solutions that's here. Okay, notice that this matrix is already in, oops, already in this reordered form where the diagonals are the highest numbers, right? So the highest number in this row is 4. This is the diagonal, so that's good. The highest number in this row is 5. That's the diagonal, so that's good. The highest number in this row is 10. There's the diagonal. That's good. So step 1 has been accomplished just basically in the way that these equations were written. But you could always, swap rows. A row that has a high leading value, you might swap with a row that has a low leading value in order to get a high leading value up at the top here so that your convergence happens faster. Okay, so now that we've got these in the right order, we're going to go through one by one. We're going to plug in our guess for X, Y, and Z, and we're going to see what pops out. And then we're going to take that solution, we're going to plug it into the next iteration. So what should we use as an initial guess? Well, it's up to you. It's actually not up to you because this is asynchronous. It's up to me because this is asynchronous. And so I'm just going to choose 0, 0, 0, right? The simplest possible thing I can think of. So I'm now going to plug in x equals 0, y equals 0, z equals 0 into my equations. These are the equations represented by this matrix. And let's just see what happens. So I've got, for the first equation, 4x plus 0 plus 0 is equal to 7. And if I solve this, I get x associated with now my first complete iteration is 7 over 4, or 1.75. Hopefully that wasn't too fast. Let's do it for y. So here's the y equation. X plus 5y plus z is equal to minus 8. Notice I just solved for x of the next iteration. So I'm going to take that x from the next iteration and I'm going to plug it into the current iteration, right? That's, basically what this says. What this says, what number 4 says, is I'm just going to solve for values. And as soon as I solve for them, I'm going to plug them into subsequent equations. That drives convergence faster. So here I am plugging in my 1.75 for x. Y is what I'm trying to solve for. Z is still 0. The whole thing equals minus 8. And so that gives me a value for y after the first iteration, which is minus 1.95. And now I'm going to solve for z. I have a value for x1, a value for y1. I plug those in, and I'm going to solve for z. And so I go through and I do that, and I get 0.835. This is just one iteration. After 3 iterations, you get down to the point where the values are less than 0.005 from the exact result, right? Which that's probably better than any thermocouple or thermistor that you're going to run into, at least from a vendor, right? Without doing a lot of extra work to calibrate them. And so that's probably a good convergence point. So so these are the exact solutions, right? At least. Huh. Okay, hang on. Let me 31. I'm just looking at there's a mismatch between this number and this number. It's not a very big mismatch, but it is a mismatch. So I need to check on that, which one of these is actually right. So after 3 iterations, I basically get to a point where I'm less than 0.005 away from the actual answer, right? Just 3 iterations, awfully fast, right? Even just 1 iteration, right? So this is X iteration one, Y iteration one, Z iteration one. I'm already at 1.75 versus 2.086, minus 1.95 versus 2.185, and 0.835 versus 0.838, right? So even 1 iteration gets you pretty darn close to the exact value. 2 iterations, even closer. 3 iterations, you're basically exact, right? So that's really just what I wanted to show is that by doing this um, reordering along the diagonal and then basically solving for a value and then plugging it in and using it in subsequent equations and then iterating on that, you can converge quite a bit faster to the exact solution. It's only 3 iterations, at least with this combination of equations. So I think that's very cool and very powerful. And so this is just, again, an example of this technique if you're ever asked to use it. Okay, so we've now got our solution, right? So this is our answer with maybe one dodgy number, which I'll check on. And remember, this was an approximation. This was not an exact solution. So we want to do something to try to verify the accuracy of our finite difference solution. So when you do something like finite element, finite difference, some sort of computational numerical technique, it's always a good practice to verify the correct numerical solution formulation by picking a node and doing the energy analysis on that node to make sure that the temperatures that you calculate, right? So basically doing this or this, if you don't have any generation, making sure that the numbers that you calculate that are surrounded by 4 of their neighbors that are internal points give you the correct and expected temperature value. So that's one way to do it. I also say here, even when finite difference equations are properly solved, results may still represent a coarse approximation to the actual temperature field as a consequence of the spacing being too big between the nodes, so delta x, delta y being too large, and the fact that we're basically taking like linearized finite difference approximations to Fourier's law of conduction, which has in it a pure derivative, right? So we're basically linearizing this derivative, and if the derivative is changing more rapidly than I can capture with a linear approximation, I'm going to miss the change in derivative with this kind of finite difference approach method. So just things to be aware of. Finite difference approximations are more accurate as the nodal networks become refined. So as delta x and delta y get smaller, you get a more accurate answer. I say here, grid studies compare coarse grids to fine grids. Okay. So how do you know that you've actually converged to like the final solution, or at least a solution that's good enough? So there's a technique called a grid study. And what you do in a grid study is you just reduce delta x and delta y by a factor of 2, right? So reduce delta x, delta y by a factor of 2, resolve the entire network again, and then check the same points on the coarser mesh versus the finer mesh. And what should happen, I say here, if grid study agreement is unsatisfactory, which means when you compare the coarser grid to the finer grid, you're not getting the same answer for individual nodes, then you have to further refine the grid, which means making X and Y even smaller. And you have to keep doing that until there's no more relationship between how big X and Y are and what your temperatures are in a particular spot, right? But be warned, right? You're reducing the size of the individual nodes, which means you're increasing the number of nodes in the mesh, and more nodes in the mesh means more computational complexity, more computational power needed. And so it's actually quite easy to let this get out of hand and continue to reduce X and Y by a factor of 2 until you have so many nodes that you can't even solve it anymore. Your computer basically runs out of memory. So this is sort of the standard technique to test whether your grid is fine enough, but just be aware that you're like, increasing the number of equations that your computer has to solve by 4 every time you reduce X and Y by a factor of 2. So just, you can very quickly get to a scary number of equations. Okay, you can also, of course, just validate your numerical solutions by comparing to my favorite, the exact solution for simple geometries, right? So if you've got some, crazy, like, potato shaped nonsense like this, right? You could actually like approximate it as a square plate or find a square plate in there, right, where you actually know what the boundary conditions are. And then you can use my favorite, the exact solution, to make sure that your computational approach is giving you the correct answer, right? So always good to check the computer. Never just let the computer blindly, trying to find my slide. There it is. Never let the computer kind of blindly just tell you the answer without doing some sort of verification. Um, okay, yeah. So that's what I say here, right? So this is another value of having those exact solutions is that you can use them to check finite difference solutions for simple geometries, right? And you've got the exact solution, so it's a helpful benchmark for finite elements. Okay, let's do a couple of examples. I think I have 4 examples here, and then we'll wrap up. So first example is we have a 2-dimensional rectangular plate. It's 1 meter wide and 1.5 meters long, and it's subjected to the prescribed boundary conditions where we have T1, right? So that's this, and this are uh, 323 Kelvin, and then T2, which is this, is 413 Kelvin. And we're asked to use the exact solution to calculate the temperature at a point of 0.75 and 0.5 by considering the first 5 non-zero terms of the finite infinite series, right? So what a cool problem, right? This is exactly like the problem that we solved before, except we're just, kind of changing the numbers around. So this just kind of gives you practice with, using the equation to find the exact solution. So here's the full-blown equation for the exact solution, right? I don't need to like solve it again because I already solved it once. The boundary conditions are the same. Theta equals 0, 0, 0, and then theta is going to equal 1 across the top. So I'm going to get the exact same result. And then we're asked to solve the first 5 non-zero terms. So I'm going to write this out in all its glory. There it is. I know that the even terms are 0, as I talked about before. So the first 5 non-zero terms are 1, 3, 5, 7, and 9. And so all I have to do is just write this out for each one of those n values because I know x and I know y, wherever y went. Oh, there it is. There's y, right? And there's x for my particular spot that I'm interested in, 0.75 and 0.5. And so I just need to solve 5 of these, right? So here I am plugging in n equals 1, and I'll get some numerical solution. Here I am plugging in n equals 3, and I'll get some numerical solution. Here I am plugging in n equals 5 and getting some numerical solution. And then here I am plugging in n equals 7 and getting some numerical solution. Last page, here I am plugging in n equals 9 and getting another numerical solution. So I now have 5 values. And as you can see, right, here they are, right? So for n equals 1, I get theta of 0.6. For n equals 2, of course, it's 0. For n equals 3, you can see it's very, very tiny, 0.02876. For 4, it's going to be 0. For 5, it's going to be very small but positive. Notice, right, these are going down by a factor of 10 every time I do them. And by the time I get to n equals 9, I'm at 0.000002 and some change, right? So this is definitely diminishing returns below the point where I just don't need to worry about these anymore because they get so small. So if I take those first 5 non-zero terms and I add them up, that's what I'm doing here. So I'm adding them up. I'm multiplying by 2 over pi, which is the coefficient sitting down in front. I get 0.38076. And I now have to reverse my theta, right? This is all in terms of dimensionless theta. I have to reverse my theta to figure out what that actual temperature is. Well, it's not too bad because I know T1 and T2, so I plug in my known values for T1 and T2. I plug in my known value for theta, which I just solved for, and out pops Txy, right? So here I am just doing it, here I am doing it, here I am doing it, cranking through, okay. And so Txy is 357.4 Kelvin. And I'm going to just make myself a note, 35, check. Normally I check these, and I did actually check this, and it is the correct solution. I just didn't put a check mark there. So I'm going to add that when you guys see the final version of the slides, right? So did I do it right? Yeah, right. I'm just looking for the temperature at this spot using 5 terms, right? So here's my 5 terms, and here's my temperature at the spot. Okay, cool. So I got that one. All right. Example number two is a shape factor problem. So, ice, sorry. So for this one, I have radioactive waste. It's temporarily stored in a spherical container buried below the air, the air soil. Oh, I get it. Okay. Spherical container buried below the air soil surface, but I give the K value of the air soil surface is 0.52. That's actually the thermal conductivity of the soil. Right, soil, 0.52 watts per meter Kelvin. So that surface at a center to surface depth of 10 meters. The outside diameter of the container is 2 meters, and a 500 watt amount of heat is being released via radioactive decay from this spherical buried object, nuclear baseball. If the soil surface temperature is 293.15 Kelvin, what is the outside surface temperature of the container? Okay, this is a shape factor problem, right? So I described this geometry where we basically have a buried sphere in soil, and so that should tip you off to go to the shape factor table and try to find buried spheres in semi-infinite solids. And lo and behold, this is case number 1, which we've already talked about, right? Isothermal sphere buried in semi-infinite solid. And so all I need to do now is check the restriction and then use this shape factor to figure out the heat flux, right? So step 1 was identify the correct shape factor. We did that. Number 2 is to consider my assumptions. So we're going to imagine this is steady state and that the soil in which this thing is buried has constant properties. The third thing I'm going to do is confirm the restrictions, right? Confirm that this thing is not too, I think it's shallow would be the problem for this calculation to give a reasonable approximation to the exact answer. So the restriction here is that Z has to be greater than D over 2. What's D over 2? Well, the diameter of this thing is 2 meters, so D over 2 is 1 meter. And that is, in fact, less than 10 meters, which is right here, is the given depth, right? So this restriction is satisfied. Z is, in fact, 10 times bigger than D over 2, so that's great. And now I'm going to just calculate the shape factor, right? So here's the equation for the shape factor. I'm going to plug in my known D and my known Z. So here I am doing that. And I end up with a shape factor of 13.23. And now I just take my shape factor and I put it into my shape factor modified conduction equation, right? So I'm looking for a heat flux, right? I think I am. Oh, no, 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 no. What is the outside surface temperature of the container? Okay. I'm looking for, I'm looking for effectively T1, right? So the outside surface temperature of the container is what I'm looking for. So I'm going to, yeah, that makes sense. So I'm going to rearrange this thing to solve for T1. So I'm going to divide both sides by S over K, right? So there's S over K. I'm going to add T2 to both sides. So here's T2 showing up on the other side equal to T1. And now I've got it all set up so that I can solve for T1. So I'm going to plug in my values. I was told in the problem statement that the thing is basically dissipating. This is like a nuclear football. It's dissipating 500 watts. Um, let's see. Oh, I wrote my shape factor twice. Ha. Okay. It's dissipating 500 watts. This is the shape factor. I've put it in there 2 times because I copy pasted too many times. So when you guys see the final version of the slides, there'll just be one of these there, 13.23. And then this is the K value, right? So that's basically this expression, right? Just in those terms. I'm going to add T2. So here's my T2. And then out pops T1. So 365 and 0.84 degrees Kelvin. Okay, and I checked against the book because this was a textbook problem, and that answer is correct, and AI agrees with me. So just kind of, just a cool little kind of afterthought to this problem. So we're talking about a buried sphere, and I actually found isotherms and um, heat flux lines for this particular case. So I say here isotherms for a heated sphere buried in a semi-infinite medium. Right? And so each one of these nearly concentric circles is basically line of constant temperature. And then these are all lines of constant flux, right? So not too bad. Okay. Um, 2 more examples. So this is another shape factor, a little bit more complicated. So we have 2 parallel pipes that are spaced half a meter apart and buried in soil. And I'm giving you the soil thermal conductivity. The pipes have outer diameters of 175 millimeters with surface temperatures of 448.15 Kelvin and 278.15 Kelvin, respectively. And then we're asked to estimate the heat transfer rate per unit length between the 2 pipes. And I underline that because I want to emphasize we're not worried about heat transfer from the pipes to the surrounding medium. We're worried about the heat transfer from the pipes to each other, right? That is an important distinction because this shape factor does that for us. If we were worried about well, we'll see in a second, the conduction of the pipes out into the soil, we would need to do something else. And in fact, I asked that. I say, without solving, what additional information is needed to estimate the heat gain of a 278.15 Kelvin pipe if the soil is at 300 Kelvin, right? So that's asking for what information would you need to solve that additional problem. We're not doing that yet, right? We're just looking at the heat transfer between these 2 pipes. Okay, so we're going to identify the correct shape factor. Hey, the jig is up. It's case number 4, conduction between 2 cylinders at infinite length. We're going to think through our assumptions. So our assumptions include the situation is steady state, the soil has constant properties, particularly constant K. We need to also make some assumptions about the restrictions because no information about the depth of these things is actually given, right? So in order to solve this, unless we use some much more complicated shape factor that actually includes some finite difference between the cylinders and the wall, L, which is the depth, has to be much, much greater than D1, which is the diameter of the first uh, cylinder. It also has to be much, much greater than D2, and it has to be much, much greater than W. I don't actually know those things. I'm just assuming them to be true because that information is not given, and I want to solve this problem, right? So these are my assumptions. Next, we're going to confirm that the problem does not violate any of the restrictions. Well, this is kind of hand wavy, but I already assumed in the previous line that none of the restrictions were violated because none of the actual numbers are given. And so this is one of those cases where you'd have to like solve for this, figure out what L is, and then go back and make sure that you're not in violation of any of the shape factor restrictions. Which I think we're not. I think it's fine to do this. I think I checked. Okay, so now we're going to calculate H. Sorry, not H. We're going to calculate S, shape factor, which is pretty intense. It has a hyper. This is how I got H on my mind. It has a hyperbolic cosine in it. So here I am just taking the kind of general expression, and then here I am actually plugging in values. What I will mention is no value for L was given. But if you look back at the problem statement, they are asking for too far, too far. If I go back to the problem, I was here the whole time. They're asking for, here it is, heat transfer rate per unit length, right? So it is perfectly fine to have, to have these L sitting in here because as we'll see on the next step, I'm going to just solve for the shape factor. So here I am doing it, right? And I'm going to just leave L in there, right? So here I am actually plugging in the values for diameter and so forth, going through and doing the math, simplifying the hyperbolic cosine. And what I end up with is 1.288 times L. Now, when I get to the next step, which is applying S into the solution, I've got S times K times delta T. I remember that S has L in it, and what I'm actually looking for is not heat transfer rate, but heat transfer rate per length of the buried pipes. And so I'm going to just divide both sides by L, right, which I can because it's sitting out here in the coefficient in the front. And what is Q divided by L? It's just Q prime, right? It's exactly what I'm looking for. So that solves two problems at once. That solves the how do I get a Q prime? And that solves, what do I do with L if I don't actually know the value because it's not given? Okay, so here I am just plugging in the numbers, right? So plugging in numbers, plugging in numbers, plugging in numbers. And what I end up with is about 110, 109.5 watts per unit length, right? So it's watts per length. And again, I checked with the book, and this is the answer the book gives. And I ran this through AI, and it's the answer that AI gives. So pretty confident that this is the right answer. Now, there's that last part, right, which is without solving, what additional information is needed to estimate the heat gain in the colder section of pipe if the soil is at 300 Kelvin. Okay, so the way that I would tackle this one, we don't actually need to like solve for anything. We need to just sort of think through how we would solve. So the additional information that's needed is the depth, right? And why? Because I can treat each one of these cylinders as its own individual buried cylinder in an infinite medium, but I don't know how deep these are buried, right? So if I knew how deep they were buried, I could actually use this approximation to figure out the heat transfer between the cylinders and that solid surface at I think it's 300 Kelvin. With the shape factor, right? So obviously I need to find the appropriate shape factor in the table, and I need to know Z, the burial depth. But once I know the appropriate material and Z of the burial depth, I can solve this just like any other shape factor type problem. Okay, moving on. We got one more. Last example. Okay, so this one is a finite difference. So I have a long conducting rod, 20 millimeters on a side by 30 millimeters on a side. It's rectangular. Um, and it has a thermal conductivity of 20 watts per meter Kelvin. And it experiences uniform heat generation. Oh no, we've got heat generation we have to deal with at a rate of Q dot triple prime is equal to 2 times 10 to the 7th watts per meter cubed. Well, its surfaces are maintained at 300 Kelvin, right? So this surface, this surface, and that surface are all 300 Kelvin. And that will become important later because we're going to apply a mesh node grid to this rectangular shape. And we're going to actually solve for, see, it says here, determine the temperature at nodes 2, 4, and 6. So we're going to actually determine the temperatures at 2, 4, and 6. And at least in two of those cases, 2 and 4, were a node sitting right next to the edge, right? So we need to know what the temperature of the edge is so that we can incorporate that into our averaging. Okay, so we're given the temperature at all of the nodes that are marked 1. Notice this thing is symmetrical about X and symmetrical about Y, right? So this is actually the center point, and it's symmetrical that way, and up and down. Each of the different steps, delta X and delta Y, to make our little regions of interest is each 5 millimeters, so they're pretty tiny. The nodes are, of course, are squares. And then these temperatures are given: T1, T3, T5. Those are given right there. Okay, so we're told to use the finite difference method with grid spacing of 5 millimeters, which is already laid out here for us, to determine the temperature of nodes 2, 4, and 6. Okay, so we're going to apply the finite difference method with the energy balance. We're going to make a couple of assumptions. So we're going to assume this thing is operating in steady state. It's pure 2D conduction with no conduction into the page, right? So no Z direction. All of my properties are constant, so constant K values and so forth, and then uniform heat generation. So heat generation doesn't change. So I'll spare you the trouble of going back into the slide deck to find the equation, but this is the equation for the energy balance method via finite difference. And all I need to do is just translate this paragraph into solutions for TMN, where TMN is going to be all these critical locations that are identified. Okay. So here's me doing it, right? So the first thing that I'm going to do, remember, I've got this heat generation term because I'm told that I've got heat generation here, 2 times 10 to the 7th watts per cubic meter. So I gotta calculate this. So here I am calculating it. So Q dot times delta X squared divided by K. All those values are given. So I plug it all in, and out pops a nice round 25K, which leads me to believe that somebody actually formulated this problem on purpose to make the math easy. So you didn't end up with like 24.2317436. 25K is Kelvin is the answer to what this heat generation term is. And then I can take that value, which I know, and I can plug it into each of my temperature expressions, right? So this temperature expression, but for each one of these individual nodes. And here it is for node number 2. Let's look at node number 2. I'm not actually sure. Oh, node number 2. You know what? We could just stay here because I actually circled them here instead of having to go back and forth. So here's node number 2, right? So how do I do this? So I'm looking at the original equation. I need the 4 nodes surrounding node number 2. So what is that? That's node 1, check. Node 5, check. 5. Node 3, check. And node S for surface, right? TS is up here. So here's the surface temperature, check. And then I'm going to add my 25 Kelvin, which again is from my heat generation, right? So that's what I calculated here. And that equals 4 times the temperature at node number 2. We do a little, algebraic manipulation. We solve for T2, and it works out to be 327.6 Kelvin. Okay. And that's verified with the back of the book and with AI. Okay, I don't know that I need to do the other ones other than to point out that the process is exactly the same. So I'm trying to solve for T4. Where's T4? Where here it is, right? And there's another one here. This rod that we're given is actually symmetrical. So you can solve for either one of these and you'll end up with the correct answer. This one has a surface here, so there definitely has to be a TS to account for the surface. But then, right, there's TS, but then it's surrounded by T1, T5, T1 again because we've got symmetry. And so that's T1, T5, T1. And then here's the 25 Kelvin from the heat generation. And then I'm going to just solve this and I get T4 is equal to 325 Kelvin, right? So that checks out with AI and with the book. The last one, same story. So here's node number 6. What's different about node number 6 from the other two nodes is that this is an interior node. It does not have a surface temperature. So I don't need to, worry about where 300 Kelvin is coming from because there is not going to be a 300 Kelvin in the finite difference calculation for this node. So here I am, right? So here's T3, here's T5, here's T3, and here's T5, right? So T3, T5, T3, T5. And then I'm adding once more that 25 Kelvin that comes from the generation and solving for T6. So here I am doing it. And out pops T6 is 339.2 Kelvin. Okay, so I got all of these to check out with the AI. So I'm pretty confident that that's right. And hey, that brings us to the end, right? That's the end of example number 4. We did all 4 examples. Cool. Okay. So, this is the final slide. So just want to thank everybody for your time and attention. And I will see you in the next one. Okay. Now I got to figure out how to stop the recording. There we go. Bye.